Hello everyone, it's March 29th. It's a new week, new Monday. Let's take a look what we have. We got 4 notifications that I have no idea what they mean. Alright, let's give it a go and then go for it. Flip binary tree to match pre-order traversal. You're given the root of a binary tree. I like binary tree, so hopefully this one will be resolved with ease. With unknodes, where each node is uniquely assigned a value. Okay, these values are unique, 1 to n. You're also given a sequence of n values voyage, which is the desired pre-order traversal of the tree. Any node in the binary tree can be flipped by swapping its left and right subtree. For example, flipping node 1 will have the following effect. So flip a node will swap its left and right tree. Flip the smallest number of nodes so that the pre-order traversal of the tree matches voyage. Return a list of the values of all flipped nodes. You may return the answer in any order. If it is impossible to flip the nodes in the tree to make the pre-order traversal match voyage, return -1. Okay, so pre-order, I forgot, is pre-order left root, right? Provides a pre-order. What's pre-order? Pre-order is visit node and node.left and then node.right. What is this? When the pre-orders go right first. Go right and then visit the node and then visit left. So it's right, root, left. Can we be more sure that this is the right way to go? Pre-order, in order, post order. In order is left, node, right. Post order is left, right, node. Okay, so Morris. So that's the thing. So it's going to be right and node and left. Okay, so that's why is it called pre-order? But this one is also different. Pre-order node right. See here, what we say is we're going to push node, and while it's not empty, we're going to pop node. We visit it first. Right child is pushed first, so that left is processed first. Huh? Wait, what? What? I don't understand. All right, this is getting me more confused. Pre-order. Oh, tree traversal. Tree traversal. Let's see. Pre-order. I forgot. What is pre-order again? Okay. In order is left, root, right. Pre-order is root, left, right. Post order is left, right, root. So we do the root first. How is this algorithm doing root first? Let me say pre-order root. Oh, this is supposed to be indented. You dummy. Should be indented this. Can we edit it? Welcome to Wikipedia. I'm not logged in. Start editing. Pre-order. That's actually true, right? It is indented. Huh. It is indented here, but it is not indented. Okay, we'll cancel it. Is it because if I get it larger? That's why. Now it makes sense. It's because of the, all right, it makes sense now. Okay, so we know. So pre-order is root left right. All right, root left right. So we have these, voyage is this. So we want root left right, but we cannot do because all we can do is flipping, and we want 2 becomes the root. And 2 cannot become the root because all we can do is 1, 2, or 1, 2. So that's impossible. In this one, the pre-order should be 1, 3, 2. So 1, next have to be 3, and then 2. So 3, 2 we can swap. So we do 1. Okay. 1, 2, 3 we don't do any. Okay. All the values are unique. All this is unique. All right. So let's take a look. Let's think about it. So what this means is we want to traverse according to the voyage, right? So the voyage says we're going to go 2 first, and now it's 1. It's already impossible, right? So we got a voyage is 1, which match our current, and then the voyage says we want a 3 and 2, and then we check the current. Current is current is left and right. It's 2, 3. So we say we're gonna swap this, and we actually swap them, and then we go to the left, right? So visit, and we'll go left. So basically, we try to follow this. Let me think. So this one is the order, right? So we hit a root, and then we're gonna go to the left tree. So we go to the left tree. We always hit the root first. So everything we see here is the root. So we go just root, like the root of the subtree, right? So root of the subtree will visit first, and then we are going to go. So if we have more, let's write a tree a little bit longer. So I kind of wanted to have a better feeling of how this in order works. So in order is going to be 1, right? And then we'll go left first. So we visit, right? And then we visit left. So coming to the left, so we go left, so visit first, and then visit left, right, nothing. So now we visit right, gonna be 5. Coming back up, gonna be 3. So that's in order. So if we follow an in order, what we're gonna see is we're gonna see root, and then next one will be either left or right, but then it doesn't tell you. It does not tell you. It does not tell you whether. I mean, hold on. I'm kind of a little bit confused right now. So basically, we try to traverse this thing, right? I try to reconstruct the tree based on this. How do we do that? So we have a root, and then the next value, you don't know if it's the right or the left, right? If the tree is tilted to the right, and then the next one, this can be the left or this can be the right. So a 1, 3, 2 can correspond to many different trees in a pre-order thing. So it could be 1, 3, 2. It could also be 1, 3, 2, or 1, 3, 2. Right? There are many different ways. So what we want to do is just to see if by swapping this we can reach here. So we hit 1, we say good, and then we see the next one. Right? Next one, it says it's going to be 3. All right. and we'll look at a current. So the next one, we don't know if it's left or right, but it doesn't matter. We just look at our current. So our current, we see the left child and right child, and we see the value and fits on. If it fits on the left child, then we say it's good. We don't have to change anything. And then we go there, right? Yes, then we go there. If it does not fit, like here, the left child does not fit, but the right child is 3. So we say we're going to swap it. So after swap, we're going to go on 3, and then the next one is 2, right? So next one is 2, but here we're on 3. We see the next one is... So we need to know what is the next one, which means, you're doing it iteratively. Is it possible? So at a root, every time we add a root, that's when we check with the thing, and if it does not match, so like we have a pointer here, then we have the current root. We say if these two do not match, then we do not have a solution. So we always make sure that they will match. And then, actually is it true? Yeah, let's say it has to match, right? And then we check the left child and the right child. And then we go look for the next one. Right, we'll go for the next one because the next one will be visiting the next one. Yeah, we're looking for the next one, and then we try to see if the next one is the left or right. If the next one matches the left child, then we don't have to swap. Right? We say we do not swap. If it matches, if it matches, then we don't swap. If it doesn't match the left and matches right, then we swap. If it does not match either, then we say it doesn't work. Okay, so just like that, if we swap, we just swap, and then we go to that node, right? We go to that node, and this pointer moving on, and then we go to that node. Then we recurse, right? Recursively see. Now this is here, and then we want to match its left and right. Now we have node 3, and now we see its left and right is empty, which means its next is nothing. So if it's like nothing, then we go back, right? We go back here. Now when we go back here, this has to increment as well, right? Because that means when we go to the left tree, now we match 3 and 3, and then nothing can go anymore. So when I go back, and actually it should be here, then we need to increment this thing. Go to the next one, and then when we go back here, we're going into this, right? We're going into this, and then when going into this and this and this, we say matching. Now it's still a little bit convoluted, right? Convoluted. So we match the left child first, and then we try to see match on the right child. If the left child, basically it's a mismatch, right? So when we're on 3, we try to start from 3, and then we say we'll start from 3, we will get nothing, and nothing does not match. And I say, oh, oops, does not match. So we go back, and because we're on the left, so we go back to the previous. Now on the right, we try to match on the right. So shouldn't we, like, when we go to the next node, we should point a pointer, so we're already matching it, right? We're already matching it. So when we go to the next, we should put a pointer here already. And then we say it does not match. So we go back, pointer's already at 2, and then we check here, we go here, and pointer, and we say we match. Where should I put a pointer? So pointer is here. Now we do all the matching inside, so we don't do it like in the next level. We do all the matching, and so the current on the right node, and then we try to compare the right node to this, and we say it's the same. So we go into the right node, and then this one also increment, and this one will return nothing because it's just nothing. It's a leaf node, and then we try to compare, and then if it's also at the end, then we say it's a match. We're good, right? So we go back, or not. And in this case, I'm not sure. I'm not 100% sure. In my work, I'm gonna try it, but it feels a little bit convoluted the way that I'm thinking about the recursion that I'm thinking about. I mean, just like it's not really generalizable, right? I don't quite feel it, but I think it's solvable. Anyway, let's try it. So we're gonna call it. We're gonna have a what? I can actually do it here. Self dot index, right? Index equals 0, and we're gonna call n equals len voyage. Okay, so we're gonna say traverse, and we give it a node, right? Give it a node, and that's about it, right? And we are going to, so in this case, if we don't compare, but we have to compare if the root is the same. Now the root is the same will be compared on the outside. Yeah. So we make sure that when we enter, the root is always the same as the root will be the same. And then when we enter a node, we're going to compare its left and right child, right? So we're going to say left, so we're going to say, so the index, what we want, the index is pointing to the ones to be compared. And now I am on a node, so I'm going to look to my left child. I'm going to say if node.left, if not node.left, no, if node.left, if node.left and node.left.val equals voyage self.index, right? This is a situation where we're all good. So we say self.index plus equal 1, and we traverse node.left, right? Yes, that's that. Now, else, Aleph. Oh, this situation is complicated. Because we have, hold on. I don't think, if node.left and node.left.val not equal to this, or not node.left, right? So these two situations are the same. That means we need to swap. We need to swap. So we are going to swap. We're going to say node.left, node.right equals node.left, node.right, and node.left. Right. We're also going to have a result. Right. We're going to have to swap. So if left is, oh man, come on. That still doesn't feel right. It still doesn't feel right. Doesn't feel right to me. Or should we do the comparison on the root? Right? We'll compare on the root, and we say if it's not the same, then we say it's not going to happen. And if we say, it is the same, right? If it is the same, then we go to the left, and this one will traverse, we'll just add, and we're going to compare the left, and if it's not the same, we come back, then we're going to just swap it and go to the left again, and if it's still not the same, then we know it's no good, then we cancel it, right? And if one of either swap or not swap is successful, then we just keep going down that route, and until it returns something that's bad or good. Like if we go left, right? We go left, and then visit, go left, always go left. And when left all taken care of, like they're all good, and coming back, we have to also go to right. And right, yeah, so I'm going to return a Boolean value. So what do we say? We say if do we have like a, or it just end? So if node dot val, if node, if not node, right? If not node, I'm gonna return false. And oh wait, it's actually not right. If not node, right? Which means we go to that's the end, right? And if not node, and we say return false, return true if self.index equals n, else false. So basically we just return self.index equals this, right? Now we know it's good, so we say if node.val is not equal to voyage self.index. Right, if node.val is not equal, then we return false. If this route cannot go. Now they're the same. So node.val and voyage is the same. If they're the same, then we're gonna say traverse node.left. And we're gonna do also in that case we shall pass in the index. That'll make it easier. So we're passing the index. And then here we say index equals this, and then we're going to say the index, right? And then we're going to say index plus 1, right? Because we traverse on the left, we need to go to the next one, all right? So we say if this is true, then we need to traverse. Oh, the index has to keep increasing. We do have to use a self.index, because otherwise, how do you know where your current index is? Doesn't make sense. Okay, so let's still use self.index, and this has to be self.index. And instead of doing this, I'm going to say self.index plus equal 1, and then we're going to traverse. Right, after traverse, if it's successful, then self.index has been incremented all along. So we say node.right. Else, that means this route is bad. So it means going left is bad, right? Going left is bad. Now going left is bad, we have two scenarios. Either the left itself directly is bad, or the left is good, but something down the line is bad. But either way, we're going to swap, right? Let's just swap. How do we swap? Now we simply say, hold on. So we say self.index, oh my god, plus 1, and then we traverse the left. And whatever it does, let it do, and then we traverse right. What it does, and let it do, and then if it fails, right? If traverse this fails, if we traverse the left fail, and say we have go bunch. So if it fail, right, then like if this is not the same, then we need to do self.index minus equals 1, because we need to go back. So we're going back, right, going back to the previous node. So we decrement the self.index. But if we decrement, that's only happening in, so every level shall if we really bubbling up, if we're bubbling up to the false, like if this one, if traverse.left is going to be false, that means something down will be false, because it'd be false, I have bubble up to be false, bubble up to be false. So okay, let's try this. So the left doesn't work, so we swap left and right. Right, we're gonna say node.left, node.right equals node.right, node.left. Right, so we swap the two, and then we're gonna traverse left again. All right. Hold on. So we say we traverse left, then we try to traverse right, and we say if traverse right is also good, then we return true, which means in this case, left and right is all good. Now if traverse right is false, then we can return false, because left is right and right is wrong, then that definitely is wrong, because every value is unique. Otherwise, if the traverse left is wrong, then we have another chance, which is to swap, right? So we swap. Yeah, this will, if it's left, then we have a closure. So here we can just do this, and then basically repeat the same thing, right? Basically repeat the same thing. So we swap it, and then res.append swap. What do we return? A list of int. So we're gonna say node.val. So we're gonna swap this. After we swap, we're gonna go left again, right? And then after we go left, and we do go right, and else, if it's still wrong, then we're gonna say res dot pop. So we just put the value into it. Now we say we pop it, because, and then we're gonna return false. So like after swap, if it's still not right, then we're gonna say this is no good, right? And this we can actually just return this, either true or false. And we're gonna swap and then do this, and then this is gonna be returned, this as well. Otherwise, I'm gonna pop it and then return false. So this is my way of doing it. We're gonna say traverse root, right? And then we're gonna return res if res else -1. Okay. All right, let's give this a shot. See what is going to happen. I am not confident at all. So we have a test case and this. Oh, we have a syntax error where return traverse right. Yeah, this is a syntax error, so it doesn't have. All right, this one's good. Let's try this. 1, 2, 3, 1, 3, 2. 1, 2, 3, and 1, 3, 2. Okay, my answer. That is not correct. Okay, so we had a problem with the simple case. Okay, why? Let's see. If we have 1 to 3 here, so we're gonna traverse root. So we go into 1, self.index is 0, and yeah, I think it's this thing probably is messing up. Okay, let's take a look. So node.value not equal, right? It is equal because it's 1 on 1. It is equal, and equal. So we do index plus equals 1. So index now is 1, and when the traverse left, right? Now traverse left coming in. If not node, well, we have a node. If no value is 2, not equal to this, not equal to 3. And then we say self.index minus. Is that where the problem is? So if it's not the same, then we return false, right? But we don't do anything about the index yet. So we comment this out. So it's still pointing here. Now we're coming back. So it's if this one will return false. Then we swap them. Swap left and right. So 3 comes here. And then we're going to traverse left again. Now traverse left is 3. It's pointing also to 3. And it's good. God, it has to be like it kept incrementing. It doesn't feel right. It doesn't feel right. Hold on. Because every value is unique, right? Every value is unique. If we hit a false and then we're coming back up, it has to work, right? Think about it, because every value is unique. So as you're going through and you hit a false and then coming back up, which means if it's like you have another chance. If it's the first one, then we say return this and we have a chance. And then if the second time it's false again, then you don't have any chance. Then you're basically done, right? Which means if this one gives, let's try. If like we don't mess, we just keep going on, what's going to happen? This probably will work on this one. Oh, it still doesn't work. Yeah, something is deeply wrong. Like you said, it as long as we have, like we can have one mismatch, that's fine. Now we swap, and then we keep going. And if we have another mismatch, and that's the end, right? That's the end. So here what we have, we point at 3, and then we go to 2, and then this gives us a false, right? We go to 2, this gives us false. And coming out, we try to swap. And then after we swap, we append the rest into it, and then we go traverse the left again, because now left it becomes right. Alright, so now it's going to be 3. So we traverse, coming here, 3, 3 equals 3. So this plus 1, now we're going to point it to 2, right? Then we're going to traverse again to the left, and the left is a none, and they're going to return false. So this one will return false. And we're going to swap, and we put 3 into it, and then go to this one none again, and this one will be none, and then it will be false again. So we return false, and we'll pop it. So going back to here, right, and then this will be false. So we pop again. That's why. So it is to handle the leaf node. How do we handle the leaf node? How do we handle the leaf node? How do we handle the leaf node? We don't handle it. I mean, we just if it's we just don't even consider, right? So basically we say if not node, right, then we just return true. If not node, we're going to return true all the time, because we don't want to consider the leaf node, because everything with the comparison has to be done on the actual node. So what if we say if not node, we always return true, right? And then when we go here, go to 3, and then it's left, and then it becomes a true. So coming back to 3, now we say, oh, okay, it's good. Then we go to the right, and this one, it will also be true. So we're now going back. When we come back, it's actually here, right? For 1, it does 3 already, so we go here. But where do we increment, right? We need to increment. Well, we increment here, and then we match here, right? And when we match the left, And now we need to go for the right. So we increment to match left, right? And then if everything's done, coming back, and then we need to increment to match right. So are you saying that we have to do like self.index plus equal 1 here as well? And we need to do this one here. Man, this just looks so convoluted. I feel like there gotta be a simpler solution. This? Nope. Index out of range. That's not good. No, I want to take a step back. I feel like we're not doing it right. Okay, so the index is actually how many steps we've taken, right? So the first step, second step, third step, right? So we are on step 0, and then we compare to 0. And if any comparison is not right, and we have a chance of swap. And if after swap it's still not right, then we say that's it. We're done. Okay, so here is the case, right? We compare the first one, the root, compare by itself. And if it's not good, we immediately return. And if it is good, then we go into the root, then we go left. All right, so current step, we have current step. And then we compare. If the left is not the same, then we swap. Then we compare the left again. And if both fail, then we return false. Okay, so this is, I think I'm going to write this one again. Now, I'll be back. Bless you. All right, I'm back. All right. Just say I'm gonna redo this. I'm gonna use step as the index. So instead of having an index here and trying to figure out how to increment, decrement index, we're gonna do step. So step is going to be our index. So I'm gonna say if node.val equals not equal, right? Not equal voyage step. And then we're gonna return false, right? That means it's a mismatch. Otherwise, if they're the same, then we are going to do traverse node.left and step plus 1. And after we do that, we need to know if they all match. So if they all match, then we're going to return traverse node.right. Oh, what do we do here? That's the problem. So we need to have the current step. So we can return the step, right? We can return the step. I mean, we can return the step. So instead of return Boolean value, we return the step. And okay, let's try. So let's say we return an int, and that's going to be -1. And then we say this be current step. Right, current step equals this. And we say if current step larger equal to 0, then we're going to traverse the right current step plus 1. And else, if current step is smaller than 0, which means left is not working, then we say rest.append node.val, and then we're gonna swap node.left node.right equals node.right node.left. After swapping, we're going to say again current step. So we say current step is equal to this, and we say if current step is larger equal, so it's the same thing, right? And then we're going to traverse on the right, else, which means the current step is smaller, so we swap it, and still now we're going to return -1. So it's going to fail. And we also going to say rest.pop and then do this, and then we're going to start with a 0 step, and we're going to return this. I feel like it's the same. I don't know. It's just man, I'm not in my best today, huh? I feel like it's the same. None type has no. So we have another issue where we enter the so we can avoid that. All right, let's avoid the consideration of this. So how do we avoid it? Now we can avoid when we do the left. We only traverse the left if I can say if not node or this, then we return -1, right? Which means in that case, but the current step it has to be smaller. But we need. Oh man. No. I still feel it's not right. I still feel it is not right. and this we didn't even return anything. Oh, yeah. No, we shouldn't return this. No, we should not return this. We shall return the step. We cannot return the step. There's a step. What do we return? We return the current, the step that reaches this node. So I am at a node, right? And I know the number of steps that it takes to reach me. And I say I'm going to look to my left, right? And if I do not have a left, I am going to look to my right. So I know my current step. Let's think again. I know the current step, which means I know the index, right? Now I can go to the left, and it depends if the left it does exist, and then we traverse the left, right? And we also want to know, but that's no, it's just the index is not right. The index is not right. Hold on. Think again. Every time we consume the voyage, right? Every time we consume the voyage, we can pop it. Pop left. Why? Because every time we visit it, that node, because everything is unique. Everything is unique. So every time we visit, we can pop it. Which means it is possible to keep a central index and just keep incrementing it. So we don't even have to consider, like we can keep incrementing because and then all right, I'm back again. So what we say is we can just keep incrementing the index on the voyage. Because if we cannot, then that means we just it's wrong, right? So as long as every time we find that there's a match, then we need to increment, right? If it's a match, then we increment, and then we try to see if we can find another match. So we can go left. So again, we think about we're at a node and we have an index and we see if they match. If they do not match, then we return false. If they do match, then we increment the index, then we go left. And we go left, and then we wait for the result of the left. And if the result of the left is a false, right? So there are two scenarios. One is the left itself is wrong. If the left itself is wrong, then we swap, and we swap and go left again. And if it's still wrong, then that's wrong, right? Because I go left is correct, and then something wrong happens on the left subtree, and if it bubbles back to me, then it is a clear sign that even if you swap, because even if you swap, it's not going to work. Which means if we go left and okay, so here's the new idea, right? But again, what do we do with the empty node? If we if we encounter an empty node, what do we do? Do we like handle it? Where do we handle it? So this is thinking like if we have a left. What if we don't have a left? If we don't have a left, then we just go right. It's the same thing. And if it's wrong, then now if we don't have a left, then we have to swap. That's not correct. It doesn't really matter. I mean, yeah, it's the same. If we don't have a left, then we have a right. Or if we only have a left, we don't have a right. That doesn't matter. You swap or you don't swap, it does not affect, right? Because we go left, and if it's no, we go right. So it's the same, right? It's the same. So we will, if there is left, we go left. If there's no left, we go right. And what if there's no right? What if there's like a leaf node? What do we do with a leaf node, right? So we're here, and we compare with index. We say it's good, and I'm a leaf node, so I just return true, right? The leaf node is good. Like we don't worry about it. Okay. Where do we increment? So every time we increment, we'll go to the left. And as we go, the index will increase. And then when we go to the left, when we go to the right, we need to increment as well. We go to the right. Okay, so let's try it again. So I had just all kinds of ideas, and then just doesn't work. So we say if node.val is not equal to self.index, then we return false. Right? That means just this one is not working. Otherwise, it's the same. Now it's the same. We're gonna increment index first. Now we're gonna try left. So we're gonna say if node.left, we have left, then we say traverse node.left. Right? We traverse node.left. Now, if traverse node.left succeeds, which means if traverse node.left succeeds, and then we say self.index plus 1, then we're gonna return traverse node.right. Else, if node.left it does not have left, then we directly say we're gonna return traverse node on right. Okay, so that's that. And if, right, we'll also have a else. So if traverse node dot left, it fails, and that's when we're going to do the swap, right? So swap is going to be like this. Now, after we swap, if node dot left, oh man, when we swap, if node dot left, we try the left, and the left fails. Now, when it fails, there are two scenarios that it fails, right? Either it fails immediately, or it fails like down the line. What I say is, it fails down the line, even if you swap, it's not going to work. Only if it fails immediately, then swap will work. So we say current index equals self.index, and then we increment self.index, and then we do this swap, and then not swapping. We're gonna say if self.index equals current index plus 1. All right, then we swap. Else, and return false. Now, when we swap, we do this, and then we do basically the same thing. We say we're going to traverse. We're going to traverse on the left again. So we're going to traverse node on left again, and we say if it succeeds, then so we swap it, and then if it's good, then we do self.index plus equal 1, and return traverse node on right. Else, if it failed, then we say rest.pop. It means it's not working, and then we're going to return false. All right. And alright, this is our new one. I'm still not 100% sure. I just feel like I'm stuck in a place that it's hard to describe what it even is. Now we have this issue again. So we didn't check node on right. So we have node on left, but every time we try to do this, we don't have a node on right. So which means we need to check node on right. So we have to check node on right. So if we want to check node on right, if node on right exists, we do this. If node on right does not exist, which means the current one is a leaf node, right? So if node on left, well, if node on left, if the node has a left branch, and then we do have to check on node on right. Okay. So if I cannot go, so there's no node on right. Right? What does that mean if there's no node on right? It means so if we just keep going node on left, don't go node on left, and then we reach the end. No, let's say we don't reach the end, we have one more. And then if it succeeds, node on left, no node on left, then we try node on right, and we say it also doesn't have node alright. Then we just return true, right? Like if it's a leaf node, and we try to traverse the right node. And if the left node does not exist, we try to go to the right node. And if the right node does not exist, then we are on the leaf node. What do we do if we're on the leaf node? Now we always return true because this is true. So if we are on the leaf node, then we always return true, which means I'm going to say Aleph node on right, and then always return true at the end, which means if it's a leaf node, we always return true. And in here, if node on left, we're going to traverse on the left. And if traverse on left is good, and then we also need to see if we can traverse on the right. If I don't have right, if I don't have right, then we just say it's good, right? If we don't have a right node, if I only have a left branch and everything works and there's no right branch, and it's actually fine. So it's gonna be if traverse, and then we say if node on right, then we traverse. If there's no node on right, then we return true. The same thing here, if traverse on the left fails, and then we say whether we can swap. And then we say if we can swap, then we swap. If we cannot swap, we just return false. So now we swap. After we swap, and it's just one level, right? And after we swap, and we have the same issue, we have to check on the left node, right? So we still have to say if node on left, right? If node on left, then we're going to traverse this, and we say if node on right, then we traverse this. There is no node on right. If there's no node on right, yeah, that's fine. So this is that, and then if here, so if we traverse left, fail again, so we swap and fail, then swap does not work. Now if we don't have node on left, all right, so what we're saying is we go left, and then we say we need to swap, and we swap, and we find out after swap we swapped in here is also a bad one. So if this, then we say else, we're going to return false. That is very, very convoluted. Does this one work? Hi. Ay. This is too complicated. It just doesn't feel right to me. It doesn't feel right. We have an order, and we have index, right? So if on the root, we're going to compare to the index, compare to current index. If it's wrong, then we say it's not good, and we return false, right? And then we say if it's true, that means the current one works. Then we look into the index, the next index, and then we try to go left. Now when we go left, there are two scenarios. Either we have a left or we don't have a left. If we have a left, then we try it. We go left. If we and then we go left, and there is a scenario that the left is um, I feel like it's here. It has to be. If self.index is, so we do swap. So after we swap, now we do have to plus equal to 1, right? So we go left, and then left we already increment the index. And then we do whatever is on the left, and then this is what tells us if it succeeds or fail. So we say if it succeeds, then we're gonna go right. And we have to increment on the index when we go right. Why? Because when we look at the left, if left is because we do increment on here already. Look at here, we increment already. So on every time we visit, we'll already increment, right? Which means after we traversal, we should not increment. So we're gonna remove all these. Yes, we're gonna remove all these, and we don't need this because we already incremented. So we'll try again. This time it works. Let's see. Oh, this one's not gonna work. I think it's gonna return -1. Yeah. Hold on. If we pop. Oh. I mean, I can do a flag, right? I can have a flag, but that just feels stupid to me, right? It just feels stupid. Well. I think what I can do is instead of checking this, we're gonna return res. We're gonna return res if this is true, else gonna return this one, right? So basically, because the function does return a Boolean value, okay, then if we do this shall return -1, and this return 1, and if we do 2 here, then this shall return an empty, not a valid integer. Oh, too fast. Alright, let's try. I'm not confident in this one. Yeah, it's not right. No. It still feels just convoluted. Very convoluted. Gotta be a easier solution. So I'm here, right? I'm here, I'm with an index. Then I go left, right? When I go left, now I'm in left, and I have the index as well. And I check the index, and if it works, then I keep going. So basically, what I want is I'm given a node, and then its branch. So we want to know if it all matches or not. So we go left. So we traverse all the left, try to see if everything matches on the left, and if I'm all match, then I'm going to traverse on the right to see if I'm all match on the right side, right? If both match, then I'm going to return true. That means a match. If the left doesn't match, and we can swap left and right, and we're going to match the left again. And if it still doesn't match, then we just say it's not matching. So, and the case of none is, we can always say none is matching, because none is not really part of the conversation. So what I'm saying is, if not node, we're going to return true. If this, we're going to return false. And I'm going to say, let's make it easier. So we're going to say incremented, right? And then we say if traverse node.left is true, then we're going to return traverse node.right. Else, if traverse node.left is not true, then we're going to swap, right? I'm going to swap, and then we do exactly the same thing. If traverse, and then no, we're actually going to say if this, and then we're going to return false, right? So this is a new one. Actually, I changed this as well. So the final can be like this, right? Okay, let's try this one. Oh, it should be 1, 3, 2. 1, 3, 2. Okay, let's try this. Let's try 1, 2, 3. See what happens. Still using the old test case, right? Let's submit it. If it's wrong, then it's wrong. Oh, we got it this time. Wait, I mean, I don't know. I don't know. It seems pretty easy, right? It is easy. It's I don't know, man. I have no clue why I didn't, like, all the convoluted things that we were thinking about. Man. And it didn't even pop. I didn't even pop anything. Oh yeah, you don't have to pop. Yeah, because we are relying on this. So even if we put something in res, it doesn't really matter, because if the final outcome is a false, then we just say it's not going to work. And yeah, that's it. I don't know. I mean, it's not that hard. Yeah, I feel very bad that we failed this one, actually. Yeah, it's like, all right. Well, I had I don't know what happened, but my initial thinking process was extremely convoluted. After clearing my mind and come in mind and rethink, I was able to reconsider the essence of the recursive relations. It turns out there are two aspects. Two keys. First, the index on voyage only increases. This is because all values are unique. So there is no need to backtrack. Second, any empty node shall be considered a match, because empty nodes do not contribute to the matching. Contribute to the matching of voyage. With these two keys, the recursion is easier to implement. We check the node's value with the current index, with the current value specified by the index in voyage. If they're not the same, we return false. If they are the same, we proceed by traversing on the left. If the left traverse fails, we have a second chance of swapping, and then traversing the left again. If the second left traverse also fails, we return false. Anytime a left traverse succeeds, we proceed to traverse a right branch. And that's it. This runs ON because each node only visits once, and we run at 36 milliseconds with 61% ranking. Yeah, it's fairly easy. I don't know what happened. And oh, this one I didn't even use it. I don't understand. It was weird. I blame this on this like a really awful time. Probably have solutions. Yeah, probably have solutions. It's very simple. I don't know what happened. DFS. Yeah, let's see. Flipped. If node, the value not equal to this, flipped equals this, and return. Then if node, we're gonna increment this. If this is smaller, and node on left and node on left are not equal, append. Okay, let's do it again. So we check node with current index, right? That's correct. And after we check the +1, so basically it's the same so far. And we say if it's still within, and node on left, we have left, and node on left of value is not equal to this, then we're going to flip, which means we're going to go right first and then go left. Else we go left first and then right. And we do this, I would say if self.flipped, and then this one 0 is -1. Do this. How are you so sure that it's going to be at the 0 position? Oh yeah, because we're reassigning this to this. Ah, you see that? This is the swap. You don't even have the swap. You just do it the other way. Huh. So we go left, we go right. Yeah, now it just seems so easy. So which means I don't have to do this. Yeah, there's no swapping. All we need to do is we're gonna go right first, and then here we're gonna go left, right? This is essentially swapping, right? Yeah, this is essentially swapping. We'll go right first and then we'll go left. So this solution is the same idea. We reset flipped, so we handle flipped, right? And then we decide whether we want to go to the left branch or the right branch. If this is not, we'll go to the left and go to the right branch. Otherwise, we'll go to the left branch. It's just to mislead. Ah, yeah. I didn't even think about this. DFS, global integer, If current node is no, it's fine, return true. If current is not, doesn't match, return false. Left child exists but don't have one value, flip with right child. I use stack. If nodes are right and the right is the same, then we swap. And we say if nodes are left, then we swap, then we extend, we push left, right, we'll go right first. Otherwise, we go right and left. Yep. All right, it's a bad day. It's a bad day for me. It's horribly ambiguous. Converted to the binary tree. The input array is pre-ordered, and yeah, it is, but that's not the point. That's not the point. It just as long as it can work. Of course, children are carried. Of course, children are carried. All right, there's no need to see other solutions. I mean, our solution. This is not bad. I mean, this is not bad at all. It's just the journey to reach here, an hour and a half. Man, it's a bad day for me. It's like the performance. My performance is not consistent, right? Someday I feel it. Someday, like today, it's just it's tree. I mean, for cry out loud, I like tree. It should be one of my strong suits, but for whatever reason, today's just it's not working for me. It's not working for me. All right. Anyway, that will be it. That will be it for today. It's late. I still have some class to catch up. I'll see you guys tomorrow. Adios.